Dobar dan i dobrodošli na balkon. Ovo predavanje će biti vezano za fraktalnu geometriju i programiranje u Javi, a cijelo predavanje ćemo održati na engleskom jeziku. Fractal geometry and programming in Java. Today, just for you. We are going to begin in a second. Okay. Once again, good afternoon, everybody, and welcome to Fractal Geometry and Programming in Java. I'm going to give you an introduction to chaos theory and complexity, a new kind of science that has been ruling the world since 70s of the 20th century. Then we'll move on to the exploration of video feedback fractals and the program that I'm currently developing. Chaos. Chaos is a mixture of randomness, irregularity and regularity. Nature is chaotic. It is both ordered and disordered in time and space. Chaos, alongside symmetry, is the key to its beauty, novelty, and wonder. Chaos is produced in deterministic processes of nature, such as the calculation of the logistic map. Here we see the logistic map or the logistic equation. It's an iterative equation that begins with a fixed value of parameter r and x0. A logistic map is deterministic because it always produces the same result for the given input. If we repeatedly calculate the new result by using the previous result, we can obtain ordered or overall chaotic behavior. So here we can see a plot of this map or equation over time. In one aspect, it is ordered because all the values, output values, fall onto this parabolic curve. However, if we consider its time series or the signal that it is outputting, we can see that it is unpredictable or random. So for certain parameter r and initial value of x0, the logistic map produces chaotic results. The signal that you see... I'm so sorry. For certain parameter r and initial value of x0, the logistic map produces chaotic results. The signal that you see plotted below never repeats itself. And yet it exhibits some degree of order, since all the values fall onto this parabolic curve. At the high school, they teach us to analyze this sort of equation as a parabolic curve. In an analytic sense, it is a quadratic equation, but when we use it as an iterative equation, it's actually the source of endless novelty and chaos. Well, is there any rule to it or any law? Well, yes, the mathematicians proved that any infinite loop, such as this one, the iteration that calculates a map in discrete time steps or a system of continuous differential equations in 3 dimensions, can exhibit chaos. Here in the background, we can see the famous flame fractals. They're fantastic for simulating turbulence, and they're very quick, fast to draw. Basically, I want to go back just for a second and try to explain to you one small thing. So if we interrupt this calculation and restart it, it will produce the same result again. So is it chaotic or not? Yes, it is chaotic and it is random. It's just that it repeats itself if we restart it. But if we interrupt it and attempt to restart it by reinserting the value of x, it will not continue as before because it is very sensitive to all the number decimals contained within the parameter x. I'm sorry, variable x. So, in essence, it is sensitive to all the decimals that we use to calculate this logistic map. And due to this sensitivity, it cannot continue as before. This is called the sensitivity to initial conditions, and it is the source of chaoticity or randomness. Let's continue. Novel definitions of system are necessary. Chaos theory can give us new perspective on nature. What seems like exchange of input-output information between living organisms and nature becomes a single equation. We may view living organisms and nature as a single equation or a single system. Organisms acquire information, respond in non-linear fashion, and attain unity with the natural world. In the background here, we see a metabolic map of human organism that shows different pathways between genes, enzymes, and metabolites, demonstrating that a drug used to target one gene may have several different effects and consequences on other pathways. Emergence is how complex things develop over time by starting from only the fundamental law of nature, depicted here as a particle process diagram. Chaotic signal could be the source of ideas that evolution can refine. So, we are now going to move to another lecture, somebody else's lecture, at the TED conference, and see the famous physicist Murray Gell-Mann, Nobel-winning physicist, speak about emergence.
They follow from the fundamental theory. They are what we call emergent properties. You don't need something more to get something more. That's what emergence means. Life can emerge from physics and chemistry, plus a lot of accidents. The human mind can arise from neurobiology and a lot of accidents. The way the chemical bond arises from physics and certain accidents.
Okay, so what was Murray Gell-Mann trying to say? He's a physicist, you know, and his view on nature is that the nature is in essence quantum mechanical, which means that it rests on probabilistic nature of elementary particle interactions. But we know that even macroscopic systems that are deterministic are capable of producing randomness and chaos. And nature is in fact unpredictable and is capable of producing very interesting behavior and very rich landscapes. So let's see, where were we? This is a complicated. Can't see it. How odd this is. So let us return now to the maps or equations that we saw, in particular the logistic map. Different parameters and variables can be visualized, and these visualizations represent the origin of very, very interesting images and graphs that possess great artistic value. I would just like to mention that briefly that Murray Gell-Mann, the physicist that you saw, is the founder of Santa Fe Institute for Complexity Research. Now, we can test how many iterations are required to reach a limit of some kind. Colors shown here represent these numbers. The most famous chaotic landscapes that you see here are Julia fractals. They arise from testing each individual point of the plane. We test a coordinate as input parameter in a map equation and iterate it to see how fast the given map reaches the limit we have set. The colors are assigned to the coordinates according to the number of cycles that it takes to reach that limit. So, in a few simple steps, or perhaps I should say in a single equation, we generate complex landscapes that remind us of landscapes that we can see on the planet Earth. So here's a forest that has certain fractal properties or certain curliness, intricacy of details, complexity, as well as self-similarity, where self-similarity means that the branches are dividing into smaller branches and so forth. All forests can be conceptualized through a single simple model using fractal geometry. Maps. Maps are essentially equations that input a coordinate and map it to somewhere else, or shall we say move it to another location. So they're morphing the plane in which we find some perhaps image. And rays of light which refract through the water are a good example of mapping. Perhaps it's too complicated. Sometimes it's simpler to demonstrate the mapping with a lens, simple lens, but here an example will do with water as well. So let us see what it means to map something. Here we have a complex function f of z equals z, where z is a complex number which denotes a coordinate. And if we take this image as a plane and map it onto itself, we'd get the same exact image as the original. However, if we map it with the map minus z, we get something that seems to have flipped sides or reversed sides. So if we apply another map to a geometric image, the inverse of z, we obtain a very complicated and interesting image. Since this is a course in computer programming, you should be aware that there are far too many balcon flyers around this image, which indicates that the computer is reusing the same balcon flyer to fill the plane up to infinity, because a single poster or a flyer, as we call it, is not sufficient to cover the whole plane and to engage the viewer in this visual transformation or beauty, as we say. Well, now let us briefly jump to our other interface. And let's take a look at my program, which uses this sort of transformations to generate fractals. So we shall start here. Geometric transformations are applied here. Some call them image morphing, some call them conformal transformations. When we repeat any transformation several times to the same image, we produce very interesting fractal images. And repeating the transformation, geometric transformation, is also known as recursion. In this video, we see more than one transformation, more than one map equation whose parameters are continuously changing. And here we have some works from photographer Muhammad Dumiri. These are the mosques in Iran. They are also transformed conformally with special lenses, kind of lenses that we cannot afford except if we do programming. Very similar to fractal worlds. Perhaps it's an art form that has been present for centuries or thousands of years around here. So these image transformations that I've been mentioning are discussed in a variety of ways, and this variety is preventing us from learning and finding information online because mathematicians are using different kinds of phrases to denote geometric transformations. So there are conformal image mapping, projections, projection maps, image morphing, and you cannot even discuss it with mathematicians unless you pick a mathematician who studied it in a certain way. Well, now we'll move on. We have a little bit I am not sure how to describe. We have a really complicated presentation mode here. Oh no. Yes, we shall have a look at this here art. I'm going to now move on to the classical video feedback art. Video feedback art has been present for around 100 years, and it's the source of fractals as well that are occurring when we point the camera at the TV screen. And this is a situation in which the image is transformed many times recursively. So let's look at some of the works from the local artists who use this technique today.
The following is a brief demonstration of my specific explorations in video feedback. It starts with a video projector on a white wall. This camera is wired to the projector and then pointed at the same surface as the projector. The result is a video feedback loop. Every change in the angle, zoom, or other settings of the camera is replicated in the image many-fold. These kinds of effects were discovered soon after video became readily available.
Now here's a group from Europe whom I met a few years ago at this very place. They had their performance. They wired the graphics adapter back to itself and used OpenGL to transform a visual image, and this is a video feedback in a different kind of way, the one that does not really include a camera or the screen, just the graphics adapter. Telco systems performed at the Video Medea Festival. And this is an art form that uses a conventional camera, screen, and a mirror. What you see right here is the mirror image. You can test these things using a separate video, webcam and your computer screen. So for all those who are interested in learning more about these linear transformations, the so-called linear geometric transformations, they can visit this web link down below. And what you see on this image is a TV set positioned in the corner made of mirrors. And it is quite difficult to grasp what is what in this image, but it's the case. It is what we're producing is a kind of a fractal tree that has this bluish look because of the light amplification, repeated light amplification through the video feedback loop. Okay, I want to illustrate you more about these linear transformations. I'll see if I can. The linear transformations occur when we, for example, mirror an image. So this axis here serves as a source of a geometric transformation, and this axis here also serves to produce more fractals. The linear transformations are really easy to define, and here it only takes three pieces of data, the position of these 3 points. All right. So let's move on to my program, Perceptron. You will notice that it has some degree of similarity to other video feedback programs, and here's how it looks in nice color. Oh, colors, yes, it's black and white. This is the default setting. It is the source of video feedback fractals, and it's currently unique in the whole wide world. So I'm going to show you a little bit of what I recorded in it before coming here. So here we have a persistent banner or a title, more in the world than meets the eye, and the geometric transformation in question is simply the mapping Z combined with some other maps for special effects. This is a series of different videos, short, connected. It can input a live video stream from the internet or from a webcam, and the only stream that I can input right now is the CNN International, which is because I do not really have any internet television subscription. So you will forgive me for presenting you the CNN news, but this is all live imagery in a sense that these animations were created in real time. This is real-time graphics, and it is the program itself is designed in Java. The latest version has been compiled in Java version 8. Here we see that Perceptron can input the Facebook stream and display it for me. The recording is perhaps not so good because it is compressed, highly compressed. This is the development environment IntelliJ IDEA Community Edition. So how does Perceptron work? Well, we're going to hurry up with these explanations. So it's a program written in Java language for Java platform. It's a virtual computer that runs on all operating systems. Right now it has been tested in 3 operating systems. It began in 2007 as a sort of a student college work by Michael Rule, and I continued some 4 years ago thereof. I've been studying it for 2 years and writing it for another 2 years. It's currently hosted at SourceForge.net. Perceptron is a Java Swing application, which means that it uses Swing library to display windows. Right now, Java FX will probably replace Swing, but Swing will continue to be updated. It's a new kind of new way to display windows and stuff. Perceptron renders buffered images using graphics 2D object directly into a JFrame, but with graphics translation methods to fit the image inside the window. And it is possible to use OpenGL alternatives for graphics, and of them all, only JMonkey is amazing. Everything else is silly. And JMonkey is absolutely phenomenal. So I'm trying to position this slide in here. Okay, so Perceptron uses graphics 2D object, and it's an active rendering application that is similar to the game engines or games as programs, and as such it has an infinite loop that runs in a separate processing thread apart from the Swing's event dispatching thread, which updates the window contents. So you need to run all the window components using the invoke later method, but the active rendering loop is run separately, and that does not always work perfectly. So we use a small hack to prevent dialog problems in Windows by making the main class extend JFrame class. So the whole program begins with this sort of voodoo statement, throughout the years, the only difference between Windows and Linux was in the backslashes, in the way you denote paths to files. But now there are more differences this year. So OpenJava for Linux is more resilient to code that breaks the conventions of how you run different threads and stuff. It's resilient and faster. OpenJava exhibits unexpected behavior when taking screen snapshots, and it works faster than the time it takes grabber window to hide itself. A mysterious property that is probably some kind of a bug. OpenJava for Linux is faster than Oracle Java for Windows, perhaps due to OS response to high-quality graphics settings such as these. Those are the so-called rendering hints, if anyone is here interested in programming Java at all. Oracle Java for Windows has a terrible bug in it. It runs at lowest CPU utilization level with some versions of HTI, Radeon graphics drivers. So there could be companies around the world that are running the applications at like 1.4 gigahertz instead of 4 gigahertz, because someone is updating their drivers, like graphics drivers or power options in Windows, and it's open to really low performance in Java, and it's been going on for a long time. Right now, I don't have these problems in my desktop computer, but it exists. It's about the CPU scheduler and the power utilization of Windows. It doesn't happen in Linux. Perceptron doesn't use synchronization, which means that it's we do not use synchronize keyword to synchronize any elements of the calculation. In this way, we accomplish 30% greater speed. So how does perceptron work? Perceptron operates with integer numbers arranged in tables. All the tables possess the same format. This is the table 1. In essence, it's a coordinate system. Each element is a number pair or a coordinate number, also known as a complex number. So if you're a mathematician, you will know that you can write it down like this. This is the matrix notation, and notice that the indexes are designed for mathematicians, while programmers use different indexes. So here would be Z00 and not Z11. So the table 2 is of fundamental importance. It is the table that contains pre-calculated values of complex function f of z, where z is taken from the table 1. Which contains the coordinate system that we wish to use to draw fractals and other things. So, for example, if f of z is the inverse of z, which means this, then we take each point from table 1 and calculate z new once, store it in the lookup table, and never calculate it again until we change the map or equation. Table 3 is the gradient. It is a simplified image with reduced data content. It's just black and white from 0 to 255 shades of gray, from black to white. And the table 4, which is about to appear, is the bailout matrix. The notation seems complicated, but it is essentially a table that stores information whether the given a value in the lookup table is very big or very small. If it's bigger than the limit circle that fits within the screen, then we say, oh, this is bigger. But if it's smaller, then we say, oh, it's smaller. So we know for each value z from the lookup table whether it is beyond the limit of a circle that we define. Tables that contain pixels are images, and we have two of those, the screen and the temporary screen, or the buffer. So all tables that contain pixels are images. By pixel we mean color, and color is stored as integer number. For example, if this is the integer number, it is divided into 3 sections. Each section denotes the value of the color, red, green, or blue. I think so. You need to know these things if you want to program graphics. You need to use integer numbers because it's fast, and it's built into the Java language. All tables possess the same format. They're squares, okay? They're the simplest to work with, but for speed purposes, each table is stored as a single long array. So you cannot have a two-dimensional table. You need to have a very long array for speed purposes, and then work everything like that. So this is the most intriguing and the most complex slide that you will see today. This is the perceptron algorithm. It stems from the video feedback cycle, as we have seen examples that use camera and TV screen. So we have the screen here, and we have the buffer, or the temporary screen, and all the visual flow goes from the screen to the buffer and back, and in between there is a transformation going. So if we start by opening the first pixel of the buffer screen, we say, oh, what are we going to put here? We are going to put the color that we find at the screen, but where? At the location denoted by value z new, which is stored in the lookup table at the same index location as the buffer index that we are trying to fill in. So we read the same index position in lookup table, bailout matrix, and gradient. So all these tables are read and written in coordination. We apply a single index, and the single index is and the same index is where we find the value that goes into the equation. And then we read the color from the screen. So we write this to the same index position in the buffer as. Let's see how it goes. At the location z new at the screen, we read the pixel from the screen. And we read this value z new, it's a fixed value from the lookup table. If the z new location is within the limit circle, we color invert pixel found there, which means that we switch from red to blue, or perhaps from white to black, or from black to white. Otherwise, if z new is outside of the limit circle, we mix its color with the color of the gradient, and it becomes mixed. We dress the image found at the screen in the image of the gradient and color invert it. If z new location is beyond the screen's edge, we use linear transformation to contract z new location and read pixel data nonetheless. So the linear transformation refers to this here. If the z new location refers to something that is beyond our memory size, the size of the screen, we use some silly transformation to reduce or contract that number and read the information from the screen nonetheless. So we get a lot of copies within copies within copies of everything found at the screen. It becomes so complicated that it is silly. Once I went to the college to discuss this with an expert in differential equations and chaos theory, and we could not discuss it, even though he is an expert and I made the program. So it's not like I'm invented really these shapes. They simply appear naturally. All the complex shapes and fractals that we see in perceptron. So let's move on to some more analysis. This is the similarity between perceptron and the classical video feedback. It's basically classical video feedback has this sort of image within image within image appearance, and perceptron has contours within contours within contours that are circular. And the reason why they're interchanging colors is because in each iteration we color invert everything that was found at the screen. So it's flickering all the time, and also this is the generation 1, this is generation 2, this is generation 3, 4, 5. So depending from the frame rate, you have this sort of age of fractal as you go inwardly. It's more aged. Here we see different presence of different transformations. This is the map Z in the first row. This is the transformation Z, and these are the linear transformations emphasized that show the contraction of the off-screen point back to the screen surface, which generates this sort of fractal structure. And here in the second row we have the map Z squared, which is nonlinear. It is the source of Julia fractals. This is Z squared, this is Z on the 4th degree, and this is again Z squared. So these are the type of graphs that perceptron is generating. You can insert color, but these black and white images are important from artistic standpoint and for analysis. And this is a slightly different case study. Here we load a fixed image and transform it without adding the interchanging contours into opponent colors, and we apply different bailout or boundary conditions. So here we have the limit circle, but here we have a limit to rectangle, and the limit something else, and limit again something else. So some other shapes are used as limit conditions to generate the bailout matrix table. My comfort has been slightly reduced here over the intricacies of the presentation. So, optimization possibilities. Always look for experienced people, or otherwise you will die. Die alone, and you will never realize your dreams. Look for program examples. Go to college. Take somebody else's homework, because if there weren't for the Michael Rule, who was a student somewhere in the USA and who had a homework, I would never learn about this sort of programming. It gave me a reason to begin to work, and it gave me really meaning of life, because I've been a developer for a number of years, and I know how to build really interesting graphics applications now, because I started working. I began my work with somebody's homework. Learn better programming. I have maybe 100 gigabytes of books, and they're all mostly poor quality. We cannot afford them, so beware. Maybe you won't have enough books. This one is pretty good. Herbert Schild. It is available for sale in Serbia, in Novi Sad. Use bitwise operations. See Hacker's Delight. It's a famous book that uses, that exemplifies in C language how you optimize calculations such as multiplications, divisions, and such things. It is extremely complicated, but so you have to use it as a reference constantly. And it is the same language used in C, C++, and Java. OpenCL, not OpenGL, but OpenCL is a new technology for AMD graphics acceleration. So hardware acceleration is available in Java. Google for Aparapi. It has 5 pages long instruction manuals, and it may allow or it may not allow for speed ups, because basic Java is still very fast, but if it does optimize something, you may get, for example, 5 times greater frame rate. Java 8 lambdas with parallel processing are now available, and I'm not so sure that they are a good thing. And the new work stealing pool, executor service that runs different processes and threads on CPU is available, which utilizes multi-core CPUs. I will show you 2 more things. I will have to hurry up, so you will forgive me. How will you learn the chaos theory? Well, first of all, Complexity Explorer is a website that offers free courses from the Santa Fe Institute. You should make sure that you apply for those courses. They're out now. You should perhaps try Chaos and Fractals, a book that is very suitable for all ages. You should look for some pirated books, or else there will be no books to read. Bookfinder.org is the largest underground library for these purposes. So while they exist, you should try to study from them. Graphics programming language processing is very interesting in NetLogo simulation environment. So these slides will be made available to you at a later date, so you will be able to check all these things slowly. I'm now going to leave this full screen, and I'm going to go back here. I'm going to try to explain to you what is going on here. I have a direct connection to my desktop computer. I cannot bring my desktop computer. It does not have a box. It's sort of really weird. And this is the development version of Perceptron. It runs on Java 8, and Java 8 is not available on this desktop computer. So we have to run it on some more advanced modern system. Otherwise, it looks exactly the same in Linux. But my home Linux would be necessary. This is, again, I will repeat, a little bit slow and ugly because it's through an internet broadcasting system called TeamViewer. So let's see, do we have here some kind of a control over this thing? I forgot really how to use it. Just kidding. Okay, so this is the default Perceptron. This is to the left side is the grabber window, which can grab live streams. And here we have options. There are perhaps I don't know how many options. We spent all the keys on the keyboard, and we're still adding options. So there are really tens of different options, maybe up to 100 options or more. And this is the signal that as it is traveling through the internet with some delays, it's preventing me to perhaps establish a full control. But so anyhow, you will have to download the release candidate version from the SourceForge and run it on your computer. You will need the Java 8 runtime environment. So I just want to make a brief resume. What I told you today is that we live in a new age. People do not believe anymore that science is deterministic or that nature is deterministic. Nature is unpredictable and chaotic. Chaos theory is going to be our presence and future. You can try to study it at the complexityexplorer.org. And deterministic systems are capable of producing endless variety, novelty, beauty, and other amazing things that we see around. Chaos is the source of novelty and beauty in nature. Here we had a program called Perceptron, which displays video feedback fractals. They are both ordered and disordered, chaotic and beautiful. So if I may take your questions, if any, now. Any questions?
I have one question about the integer math. So
Integer math?
yeah, you outlined that you're storing color information as a series of integer numbers with RGB sections.
Yes.
Splice it into weight numbers,
Yes.
operations of RGB. Instead of treating it as an hexadecimal, why is that such a better or worse strategy?
Well, you see, the RGB color space or color strategy is an invention of old, intelligent, brilliant engineers who used machine programming, assembler, C language. And they knew that the CPU works best when it works with integer numbers as written in binary format. So it's a bunch of zeros and ones, 32 digits in total. And the CPU works best if it manipulates bits. Tell it to change a bit or 2 bits, first bit, last bit, 10 bits, change ones to zeros or zeros to ones. It's meaningless. You don't get anything intelligent in that way. But these are the technically speaking, fastest operations that you can perform on a computer. So, in their best interest was to define all mathematical operations such as multiplication, division, or anything else by using bitwise operations, and you need those operations as well to isolate the middle third of an integer, the last portion of the integer, or the first portion of the integer, and the logic in the program that the program itself, the part of the program that works with colors, is completely unreadable. It is unspeakably complicated to the naked eye. It basically has to come from experts. So those basic graphics operations on color, using color, and pixel interpolation, pixel smoothing, because pixels are square. And if you have a chaos, you will have squares that explode into consequences. Everything would be terrible if we had square pixels. So you have to use interpolation, rounding, softening of image. You need to be an expert with color and color filters, or else you will get an explosion of chaos. It will look like a noise. They are fast when they're integers. If you're using floating point numbers, they don't really exist in a computer. They are concepts that need to be improved algorithmically. So if you conceptualize, oh, let's have some gigantic numbers. No, you don't have a room for gigantic number. You have a room for 64 digits in a 64-bit processor. So it's a little bit different with the other than integer numbers, and you cannot use really the slow math in any way. If you use floating point numbers or anything else out of this scenario, it becomes too slow. But if you use this scenario, it is as fast as C or C++ program, so it's worthwhile programming in Java. Anyone else? Something about chaos, about programming? Something about Windows? You probably hate Windows. Yes?
Well, I still consider myself as new programming. How do you handle graphics in Java? Well, you have garbage collection, you have those layers of abstraction. Does it work any time?
How do I handle what?
How do you handle graphics and garbage collection?
Well, here's the deal. In Java, there is no need for garbage collection. Basically, a garbage collector is some kind of process that runs on its own, and you never use it. We have, for example, graphics 2D object method called dispose. So if you have a graphics 2D object called object, you type a point, dispose, and you can evoke it and use it. And if you don't use it, it still works. So I'm not using it. I'm cheating, you know. I don't want to execute anything that would slow it down. But it does not slow it down. You can call this method dispose on almost any object when you need it disposed. But I don't need to dispose of anything during operation. It's all pretty efficient.
Yes, but for how long can you run it? Don't you get naturally at some point?
It's a very good question. I went to a job conversation where they asked me this question. I was refused, and perhaps I do not know the answer to that question. But the only time I had problem with the memory was when I designed the preview, the image preview method. What is it? When we load an external image, I wanted to bring up this sort of menu and to give me small icons, thumbnails. And I wrote my own thumbnail generator, and when it loads like 100 images, they're gigantic, then it would run into a memory problem. But I solved this by choosing the proper kind of queue that does not allow a simultaneous loading of many images. So you cannot afford to load many hundreds of images where each image is 10 megabytes or more. Then it will create a memory problem. You have to use queues. It's a topic of how some images sit and wait to be loaded instead of being loaded at once. So you record their names or something and wait to load them at the very last second when you need them. But otherwise, all other images, all other displays are very, very conservative. We have plenty of memory more. Yes, anyone else? This is being recorded.